Hi guys, welcome back. Let's look into an industry application of a dual disk system, which is actually a proposed method or proposed model for a part of hybrid vehicle. Let's get into it. Now, if you look at this system, you see that I have two disks here or two moments of inertia. One is the inertia of the piston, the other one is the inertia of the cylinder. And these two inertia elements are connected to each other by a torsion spring. And also, each of these guys are supported by a bearing. And for simplicity, we somehow model that bearing with a viscous friction. Okay, let's go ahead and list the elements in the system first. Inertia, stiffness, friction, my sources, and the number of ODs. Okay. You notice that I have two inertia elements. One of them is the mass moment of inertia for the piston, and the other one is the mass moment of inertia for the cylinder. So J1 and J2 are my inertia elements. Similarly, since I assume that the system has a torsion spring, okay, so I would lump the effect of stiffness in the system in that torsion spring. Also, if you look at the system, I have two bearings which are supporting J1 and J2. So B is actually my friction element. The last thing that I'm looking at is basically the inputs. If you look at the system, you see that Tn on these two sides are actually twisting the system. So Tn is my input. And at last, I would need to comment on the number of ODs. How many ODs do you think I would need to model this system? Well, I have two independent motions, yes? One of them is for the cylinder, the other one is for the piston. So I would say two ODs. Okay. Now let's go to step one, which is selecting your coordinate systems. And just bring this one a little bit down, coordinate systems. Okay. Now, two coordinate systems are given to me as theta 1 and theta 2. Note that, guys, your coordinate systems are your choices. You can select them whatever you like, okay? But I'm going to just work with the coordinate system that's given to me, okay? But at the end of the day, I just wanted to mention that this is your choice, okay? Your coordinate systems are yours, and you will choose them in your own way, okay? So now, if you look at the system from the side view, you see that theta 1 and theta 2, both of them are moving clockwise direction. Good. Step 2 would be isolating your inertia elements. So isolate your inertia element. I have two inertia elements, and I'm going to isolate them. So first, the piston, okay, J1, and next, the cylinder. Let me just bring this one a little bit to the left, J2. Just to make it a little bit nicer, I'm going to show the coordinate system on top of these ones as well. So theta 1 was going clockwise, and theta 2 was going also clockwise direction. Okay, good. Now I'm ready to go to step 3, which is my free body diagram. Okay, so step 3, free body diagram, or FBD. In the free body diagram, I would go after these forces: Fu, CSR. Okay, I would need to look for moments, torques, and the forces that they an arm with the center of rotation. Okay. Looking at this problem, you see that I have two bearings. One is here, and the other one is here. Okay. So for modeling those bearings, I noticed that only one end of those bearing is moving, which is attached to the mass, moment of inertias, okay, and the other end is clamped to the wall. Okay, so this is an easy model. Okay, so this is gonna be B theta dot 1 and B theta dot 2. Theta dot and theta dot 1 and theta dot 2 are in fact my angular velocities. Now I need to figure out the direction of motion. Yes, so if I assume that these boxes are moving in the positive theta 1 direction, okay, and theta 2 direction, the friction forces and torques would be against the direction of motion. Good? Okay. The next thing that I need to include is the externals. Okay, now look at the system. You see that on the side of the piston, Tn, this guy, is applied counterclockwise if you look at the system from the side view. However, on the side of the cylinder, Tn is applied in the clockwise direction. It sounds like you're trying to twist the system. Yes? Okay. So on this side, Tn is actually applied counterclockwise direction. On the other side, Tn is applied in the clockwise direction. Okay? Now, if you look at this, you see that external torque is also done. The next one is the weight. You guys know that weight is applied at the center of rotation. It has no arm to generate any torque for me. Similarly, the contact is a normal reaction from the surface. The extension of that guy passes through the center of rotation, so I would neglect that one too. Let's go to the next one, which is the spring force. Okay, and you notice that between the mass J1 and J2, I have a spring. So since both ends of that spring move, so I need an assumption between the direction of the motions. Yes? Okay. So I need to make an assumption, and then based on my assumption, I need to make inside the parentheses positive. Okay. For this system, I assume that theta 1 is greater than theta 2. Where did I get this assumption? It's not really important. Just make an assumption. Stick to your assumption. Okay. With this assumption, I would make inside the parentheses positive. Theta 1 minus theta 2. This is the order that I'm going to pick based on my assumption here. Okay. Now I need to figure out the direction. For some of you guys, it's very easy to look at the system and figure out the direction. Whether the spring is in tension or in compression, and then based off the tension or compression of the spring, you go ahead and figure out the direction. For some people like me, it's a little bit difficult. So what I would do is I would make a small schematics for myself, and somehow translate or transform this system from the mechanical rotation to mechanical translation. Look at this. How? I would say that this is my mass J1, this is my mass J2. And also, I would say that these two masses are connected to each other with a spring K1 or K, sorry. Now, here is the important part. I need to basically select my coordinate system for these two masses. Yes? Okay. I would look at the coordinate systems that I have for theta 1 and theta 2. Okay. Doesn't matter if I pick the coordinate system theta 1 and theta 2 to the left or to the right. The important thing is I keep the same interaction that they have with each other in my mechanical translation. How? I would say that, okay, in my original system, rotation system, theta 1 and theta 2 both matches directions. Yes? Okay. So I would pick theta 1 and theta 2 in a way that they match directions. Both of them are going to the right or both of them are going to the left. Doesn't matter. Now, okay, at this point, it's very easy for me to figure out the direction of the spring force. Yes? Since my underlying assumption was that theta 1 is greater than theta 2, then the spring force would be K theta 1 minus theta 2. I keep inside the parentheses positive based on my assumption. Now I need to figure out the direction. Yes? Okay. I would grab the pin and the hammer again, and I would pin down the one that moves less to the wall. Look at this. Between theta 1 and theta 2, theta 2 moves less, so I'm going to pin this one down to the wall. So this one is not moving, then I would move J1 in the positive direction theta 1. If you move J1 in the positive direction theta 1, you notice that the spring is going to be in compression, and when the spring is in compression, it's going to push back. Now look at this. On the side of J1 and theta 1, these two contradict each other. On the side of J2 and theta 2, these two match. So let's go to our free body diagram. On the side of theta 1, they're going to contradict each other. Theta 1 is positive clockwise direction. This is going to go counterclockwise. On the side of J2, they're going to match each other. So both of them are going to go clockwise direction. Okay? So one time more. Okay? The important thing here is the interaction between theta 1 and the forces that you establish here. Good? And theta 2 and the forces. That interaction is important. Also, it's very crucial that you keep the interaction between theta 1 and theta 2 the same as your original free body diagram when you want to establish this mechanical translation equivalency. Another thing that I wanted to ask you guys to do by yourself is I would ask you guys to do the same thing. Okay, so bring J1 and J2 here with the spring. Okay, and this time with the spring K, and this time assume that theta 1 and theta 2 are pointing to the positive left direction. Okay, and see whether you can get the same results as the one that we did here. Okay, whether you can get the same results as the one that did here. Just a small homework for you guys. Good? Okay. Let me just move these ones a little bit aside so I have a little bit more room to go after my equations of motion. Okay. You notice that my spring torque is gone. I'm actually done with that one. I do not have any rope in the problem, which means that my free body diagram is at this point complete. I can navigate to the next step, which is the equation of motion. Equations of motion. And this is my last step. Okay. For the equations of motion, I'm going to formulate the Newton's second law for J1 and J2. So the summation of the torques along theta 1 is equal to J1 theta 1 double dot. And summation of the torques along theta 2 is equal to J2 theta 2 double dot. Yes, guys? Okay. Let's look at J1 and theta 1. I have 1, 2, and 3 torques. Yes? And all of these guys happen to be counterclockwise direction, which is the opposite direction of my theta 1. So this is going to be negative Tn, negative B theta dot 1, negative K theta 1 minus theta 2 equals to J1 theta 1 double dot. Similarly, on the side of J2, I have Tn in the positive theta 2 direction, the torque of the spring also in the positive theta 2 direction, and the torque of the damper in the negative theta 2 direction. Yes? So it's going to be positive Tn, positive the torque of the spring, negative the torque of the damper, equals to J2 theta 2 double dot. Yes? Good. Okay. At this point, what I'm going to do is I'm going to keep the inputs on one side and bring all the dynamic terms to the other side, and I'll flip their signs. Okay. So this is going to be negative Tn equals to J1 theta 1 double dot plus B theta dot 1 plus K theta 1 minus theta 2. Yes? And also positive Tn equals to J2 theta 2 double dot plus B theta 2 dot minus K theta 1 minus theta. Okay, let's do the sanity check. Yes, in the first equation, if you look at the first equation, you see that you have two families, family of theta 1 and family of theta 2. For the family of theta 1, you have three members, theta 1 dot, and theta 1 double dot. All of these guys are positive. For the family of theta 2, you have only one member, and that's theta 2. That's negative. So there are no sign mismatches within the members of the family. Similarly, in the second equation, you see that you have, again, two families as theta 1 and theta 2. And for theta 2, you have theta 2 dot, and theta 2 double dot. For theta 1, you have only one member, which is the theta 1. Okay? And if you look at this, within the members of family theta 2, you have positive, positive, negative multiplied by negative, it's positive. So there are no sign matches. And you have only one member for theta 1 in the second equation. So there are no sign mismatches within the families, okay, within the members of a family in each of these equations. So you can safely box this equation.